Okay, Unit 4, Derivatives Part 3. We're going to talk about derivatives and its units, apply derivatives to position, velocity, and acceleration. Approximate a value using an equation of a tangent line. It's called linearization. Solve related grades problems, and use L'Hopital's rule to solve indeterminate form limit problems. Indeterminate forms are 0 over 0 and positive or negative infinity over infinity. So let's start with units. Units for a derivative are the units of y per the units of x, dy dx, the units of y over the units of x. A derivative, f prime of x, gives the rate of change of a function, f of x, at one particular instant in time. So this is also called the instantaneous rate of change. To interpret a value of f prime, we must include context of f of x, the original function, rate of change, which is the derivative, the instant, the x value where the derivative is taken, and the units of f prime. The key understanding is that the derivative gives the instantaneous rate of change of the given quantity at the indicated point in time. Ideally, you should use an action verb that indicates the direction of change. Here is an example of what this might look like. The differentiable function v of t gives the volume of water measured in gallons. So v of t is measured in gallons in a tank at time t, where t is measured in minutes. Explain the meaning of v prime of 5 equals negative 6. Well, v of t is gallons, then v prime of t will be gallons per minute. After 5 minutes, the volume of the water in the tank is decreasing. Say that it's decreasing because the derivative is negative at a rate of 6 gallons per minute. If C of t gives the cost in dollars measured after t hours, what are the units for C of t, C prime of t, C double prime of t? Well, C of t gives the cost. C prime of t finds the cost per hour, and C double prime of t finds the cost per hour squared. So C prime of 3 equals 40. So after 3 hours, the cost is increasing. It's increasing because the derivative is positive at a rate, C prime is a rate of $40 per hour. If x of t measures the position of an object in feet after t minutes, what are the units for x of t? Well, that measures feet after t minutes. V of t is the derivative of position, so this will be feet per minute. And A of t, we know, is the second derivative of position, first derivative of velocity, so A of t is measured in feet per minute squared. Interpret the meaning of v of 2 equals 12. So after 2 minutes, the position is increasing because velocity is positive. The position is increasing at a rate of 12, and the units for velocity are feet per minute. And a of 10 equals 25 can be interpreted as after 10 minutes, the velocity is increasing at a rate of 25 feet per minute squared. Now you might be wondering, why are we not saying the acceleration is increasing? Well, I don't know if the acceleration is increasing. I know that the acceleration is positive. It's a positive 25, but I don't know that the acceleration is increasing at that time. I know velocity is increasing because acceleration is positive. So don't get that mixed up in the interpretation. Remember, we need the context of f of x, the rate of change of f prime, the value, and then the units. The context of f of x is where students will make the most errors. V of t is the volume of water in a tank in liters after t seconds. What are the units for? V of t measures the volume in liters. V prime of t will be liters per second, and V double prime of t will be liters per second squared. So after 8 seconds, the volume of the water is 3 liters. This is not a rate. V of t is just measuring liters, the volume, but that's not a rate. So V of 8 equals 3 means that after 8 seconds, or at 8 seconds, the volume of the water is 3 liters. So V of t is in liters, so the volume is 3 liters at t equals 8. V prime of 15 can be interpreted as after 15 seconds, the volume is decreasing at a rate of 2 liters per second. And I know the volume is decreasing because V prime is negative. All right, going on to position or motion. Given a position function, its derivative is a velocity function. Given velocity, its derivative is an acceleration function. Average velocity in the interval A to B, given P of X's position, average velocity is the slope of position. So it's going to be P of B minus P of A over B minus A. And average acceleration is the slope of velocity. So V of B minus V of A over B minus A. Average velocity is the slope of position. Average acceleration is the slope of velocity. A particle is moving to the right or up when velocity is positive. A particle is moving to the left or down when its velocity is negative. A particle is stopped or at rest when its velocity is 0. A particle is speeding up if its velocity and acceleration have the same signs at that point. A particle's velocity is increasing when acceleration is positive. A particle is moving towards the origin when its position and velocity have opposite signs. And a particle is moving away from the origin when its position and velocity have the same signs. So for example, given the following position function for an object traveling in a straight line, supply reasoning for your answers, either in words or well-organized mathematics, or both, for each problem below. You may use a calculator. Let's assume t equals hours and x of t equals miles. So we're given x of t over the time interval 0 to 5. So over the interval from 0 to 5, I'm going to change my window so that my x's go from 0 to 5, and then I'm going to zoom in on my y's because they were all very close to the x-axis. See if that's big enough. Let's see what this looks like. There we go. That's not bad. Okay, the object stops when velocity equals 0. So the slope will equal 0 at these max and mins. So I can find each max and min, or I can go to Math 8 and y2, find the derivative of y1 by going to vars, over to y vars, enter, enter. I can turn y1 off by unhighlighting the equal sign. I can hit graph. And I can see it's going through the x-axis at those same points where the max and mins were. Now I think it's a little bit easier to find max and mins than zeros, but it's about the same amount of work, so you can do either. I'm going to go back and find max and mins. So the first one is at t equals 0.406. I'm going to pause this and find the other three. Make sure this is what you got for your times when the object is stopped, round to 3 decimal places. When is the object moving to the right? Well, the object moves to the right when velocity is positive, or when position is increasing. So I'm going to look back at my velocity function. Since I already know these zeros, because they were the max and mins of the previous function, I know that velocity is above the x-axis between the 0.406 and 1.364. Then it's above the x-axis again. It's supposed to be a U, actual U. There we go. Positive again right after 3, so it's 3.002 until we get to 4.571. Is the object speeding up or slowing down at time t equals 1.5? Well, we need to find the velocity at 1.5 and the acceleration at 1.5. So the velocity at 1.5 is just the y value. So if I go to second trace number 1, this will calculate a y value, and I can type in the desired x value. I can see that the y value is negative, so it's less than 0. Let's write what it actually is. Negative 0.241, so that's less than 0. And the acceleration at 1.5 is the derivative of velocity at 1.5, so I can go to second trace number 6, calculate the derivative at x equals 1.5, and we can see that the derivative is also negative. And when velocity and acceleration have the same signs, the particle is speeding up. Determine the average velocity over the interval from 0 to 2. Average velocity. Average velocity is the slope of position. So we need x of 2 minus x of 0 over 2 minus 0. So I'm going to go back to my position function. I'm going to go back, turn y1 back on, turn y2 off. This time I need the y values of position. So the y value at x equals 2 is 0.226. And I'm going to store that value so I'm not rounding in the middle. So I'm going to go to store, and I'm going to store it as A. Oh, no, that ain't it. Try that again. Graph. We need to find the value at x equals 2. Second quit, store as A. Nope, not working for me. Okay, so it's not storing that value there, so I'm going to do another method here. I'm going to go to bars, over to y bars, enter, enter. I need to know y1 of 2 minus y1 of 0. And then I need to divide that by 2, which is in the denominator. So the average velocity is negative 0.147. And the units of velocity will be miles per hour. In this case, because x of t is measured in miles. And t is measured in hours. All right, moving right along to linear approximation. Use the equation of a tangent line to approximate the y value of a nearby point. So remember, when we write the equation of a tangent line, it's only relevant at its point of tangency. So what we're doing is we're finding the equation of a tangent line. So say here at x equals a, we're finding the equation of a tangent line at x equals a, and we're using it to find a y value near a. So as long as I stay close to a, right, relatively close to a, then it's going to be a pretty good approximation. But again, it's just an approximation. Linearization is always an approximation, and we always use the equation of a tangent line at the point of tangency to estimate the y value at a nearby point. So to determine whether it's an over approximation or under approximation, we look at the concavity. If the function is concave up, then we can see that in an extreme case, we would have an underestimate. So even as we get closer and closer to A, these are still going to be underestimates, like the green line is less than the purple line. If it's concave down, then our estimates are going to be an overestimate. Right? The tangent line is going over the function, so it's going to be an overestimate. Maybe, remember, stay near the point of tangency. If we need to know concavity, we look at the second derivative. Here's an example, all worked out for you. Here's another example. Let f be a differentiable function such that f of 2 equals 6 and f prime of 2 equals 8. So I know the point is 2, 6, and I know the slope is 8. And those are the two things I need to write the equation of a tangent line. So I sub in the point to y minus y equals m times x minus x. Replace the second y and x and the slope. We write the equation of tangent line, and now we use it. So we wrote the equation of the tangent line here, and now we use it, right? This is the equation of the tangent line at x equals 2. Now we use it to approximate a point near 2. Well, 1.8 is near 2. So we sub in 1.8 for x, and we get that the y value approximation is 4.4. Pause it and try the last example. And moving on to related rates. Related rates are equations that have more than one rate or derivative. This is an application of implicit differentiation, right? Implicit has more than one variable, and here we have more than one rate. We solve related rates problems by drawing a diagram to visualize, express the given information and rates, express the asking rate, write an equation that relates the various quantities in the problem, differentiate both sides with respect to time, and then substitute the given information into the differential equation and solve for the asking rate. So here's an example. Related rates are best learned by doing. A cone is 30 centimeters tall and has a radius of 5 centimeters. Initially, it is full of water, but the water level falls at a constant rate of 1 centimeter per second. At what rate is the water draining from the cone? So we know the cone is full of water, but the water is draining. So if we were to draw a picture, then it would look something like this. Height is 30, radius is 5, and we know that the water level falls at a constant rate of 1 centimeter per second. It's negative because it's decreasing. So we're given information about the size of the cylinder and the rate in which the water is draining. What is the rate constant of height? So dHdt. Well, the height they told us was changing at a rate of 1 centimeter per second. What they're asking is basically what the question is asking for. In this case, it is asking for the rate at which the water is draining from the cone. In other words, they are asking for the rate of change for the volume of the water. So we're looking for dV dt. Well, I need to relate these two rates to each other. I have dH dt and I need to find dV dt. So I start with the volume formula. And I took the derivative with respect to both sides. So I had to use the product rule. The derivative of v is dV dt. So first times derivative of the second plus the second times derivative of the first. Sub in the values we know. So r equals 5, dH dt equals -1. So now what we need to do is express r in terms of h, because we have too many variables still. Even after subbing that in, we still don't know dr dt. So notice the two triangles created from this drawing. Since the two triangles are similar, then their ratios must be the same as well. In other words, the similar triangles formula gives r over h equals 5 over 30. Multiply both sides by h. Simplified 5 over 30. So we've got r in terms of h. So now I can sub that in for r. Find the derivative of both sides. Sub in the known values and solve for dV dt. So pause the video if you need to finish that problem. I'm going to show you the next one. Example 2, again, pause it so you can finish this problem. The work for example 3. And L'Hopital rule, we use it to evaluate limits in indeterminate form. So the indeterminate forms are 0 over 0 or infinity over infinity. So if the limit comes out as 0 over 0 or infinity over infinity or negative infinity over infinity, then the limit as x approaches a is the derivative of the top function divided by the derivative of the bottom function. So notice this is not quotient rule. It's just the derivative of the top divided by the derivative of the bottom. So before you can use L'Hopital's rule, you have to prove that it's in indeterminate form. So this step right here cannot be skipped. You have to show that it's in indeterminate form before you can take the derivative of the top over the derivative of the bottom and then evaluate. The next example, I subbed in -1, did not get indeterminate form. Therefore, we can just solve by direct substitution. And that's it for Unit 4.